On chapter 4 test, what's the conjugate acid of F minus? Well, it's the thing that F minus would form if it was a base, and it would form that. What's the conjugate acid of hydronium? It's the thing that hydronium would form if it acted as an acid, which is water. On number 2, we have a fictional acid HA and sodium A, and both are dissolved. So all the sodium comes off. So really, we've only contributed A minus. Find the pH and the pOH. So Kb for A minus is 1 e negative 5, which means that by doing this, Kw over Kb, I can find the Ka for the acid version. So we subtract the exponents. So we get 14 minus a negative 5, and we get 1 e negative 9 is Ka for the acid version. So if I write out the acid dissociation equilibrium equation, I get this. Now, we started with 0.1 molarity, because moles in 1 liter of the acid, and 0.01 moles per 1 liter of the A minus anion. So this is going to dissociate some and lose a little bit. This is going to add X, and this is going to add X from a total of effectively 0. We'll call it 0. So then we get products over reactants, the power of the number in front. But Ka is so small that there's no way adding or subtracting X is going to matter. So let's just do that, cross them out. 0.01 over 0.1 multiplies this by 10, dividing by 0.1 multiplies by 10, which means that I get this. So then when I divide this under, when I divide by 0.1, again, you multiply by 10 effectively. So this gets less negative, bigger is less negative, and this becomes 1 e negative 8. That is the value of X. That is also the value of the H plus. Negative log of that answer is 8, which means pH is 8, and subtracted out of 14 means pOH is 6. We need to get some practice with the Henderson-Hasselbalch equation, so let's solve it and get the same answer. pH is equal to negative log of Ka plus the log of the ratio between the conjugate base and the acid. So this is 0.01, and that's 0.1. When I divide by 0.1, I effectively multiply by 10, so this becomes 0.1. This, of course, is positive 9. And log of 10 to the negative 1 is negative 1. The power that I have to stick on 10 to reach 10 to the negative 1 is negative 1. And I'm supposed to add these, so I get pH equals 8, which subtracted out of 14 tells me pOH is 6. 4 is kind of an intro-level question, but the test writers do like to ask this kind of thing. Plus, I'm asking us to do some mental math that I probably wouldn't ask the intro kids to do. So we have a volume of acid and a molarity of acid, and then we dilute it by adding more water. So in the list of formulas will be molarity times volume of the first situation equals molarity times volume of the second situation. By the way, this is a little bit weird in that molarity is a measurement and volume is a concept, but I've usually seen it this way. Just to say this, a more proper way might be concentration by volume times volume, so that these are both concepts, because we tend to write formulas in concepts, and I don't know how measurement like molarity got in here, but that's the way I've usually seen it. So here's the molarity of the first part and the volume of the first part. What's the molarity of the second part? I don't know. What's the volume of the second part? Now, there's the trick, the most common mistake, because kids will put 80 milliliters. 80 milliliters was added to 10 milliliters, so the new volume is 90 milliliters. So when I multiply this by 10, this becomes 0.1, and I divide by 90. Of course, the milliliters cancels out, and this will be M2. Now, you might remember that fooling around with the calculator shows that 1 over 9 is 0.1 repeating forever. Well, so we have something similar here, but the numerator is smaller by power of 10. So the total answer then moves smaller by 1 decimal, but the denominator is also bigger by a power of 10. And when you divide by a bigger number, you get a smaller answer. So this is going to move the answer smaller by 1 decimal also. So now we've moved the answer, the total answer, from this being 2 decimals smaller over 2 decimals smaller. This is smaller. That's the obvious part. And dividing by a number that is 10 times bigger also gives us an answer that's 1 decimal smaller. So this is 2 decimals smaller. Now this is the molarity of the H plus. So to get pH, I would take negative log of that, but I don't have a calculator, but I can get something pretty good here. Let's just pretend that it was 0.001, which is 1 times 10 to the negative 3. So if I had that, then negative log of that would be 3, and pH would be 3. However, the H plus molarity is a little bit bigger than that. It's a little more acid than that, isn't it? Which means the pH comes down a little bit past 3. And so a good guess without a calculator for the situation would be something like 2.9. If you get water hotter, it dissociates more. So there is a temperature where Kw reaches this. Notice it's 0.1 E negative 15. And I did that on purpose to make people pay attention and have to do mental math. So this needs to have the decimal here, which means this got bigger, so this must get smaller, which means it's really 1 E negative 16. So the pH, of course, is the value of the H plus molarity. And we know that these will be equal and they must multiply to be Kw. So these are x each, so x squared equals the new Kw, and the square root of E negative 16 is E negative 8. Remember, we take sort of half the value there, half the absolute value anyway. I understand that that's not actually half. Half the absolute value maybe is a better statement, but retain the sign, and that is the value of the H plus. We take negative log of that answer, and that would be positive 8, and that is the pH in those circumstances. I know the molarity of my unknown weak acid, and I know the pH is 6. So to get Ka, what I really need is the H plus molarity. So inverse log of negative value of pH, and that's very important, negative 6 will give me 1 E negative 6 for the H plus molarity. I'm also going to point out that I wrote this on purpose so that we know the molarity is this at equilibrium. It has a pH, not it generated a pH. This is the molarity, and I don't have to mess around with minus X and so forth. This is the H plus, and therefore this is the A minus. So I can generate Ka by products over reactants, the power of the number in front. The coefficients are both 1, so they're both to the first power, but then they're multiplied by each other, which is how I get the squared term. Divided by the molarity of the acid gives me this setup. This squared is 1 E negative 12. Divided by this means I subtract the exponents, which gives me E negative 9. 1/5 is 0.2. Keep chugging along and don't just give up with mental math. And when I need the decimal to be in scientific notation of digit dot, the decimal moves over here. This got bigger by 1 decimal point. This must get smaller by 1 decimal point, and this is Ka. HSO4 minus is amphoteric because it certainly has an H to give, and people will notice that it's negative and say, well, it could take an H, except that you would be forming H2SO4, which is a strong acid, which can't be formed in water because strong acids by definition come apart in water 100%. So by all logic, they can't be formed. However, it can donate an H, and that would make an acidic solution. On 8, we have 0.001 moles of this diprotic fictional acid in 1 liter of solution. So the molarity is 1 E negative 3 to get started. Now, the real trick to this is dealing with the KBs and the KAs. So here's my acid with 1 H on it. Here's the second one. Now, is this one coming or going? And the answer is maybe either one. So if this comes on, it's the second one on, right? So that relates to KB2, the second H coming on. However, if it leaves, it's the first one going, which means that it relates to Ka1. So we convert Kb2 into Ka1, and this would have been the first H on, which means it's the second one off. So Kb1 converts into Ka2. We can do this in our heads because we can say 1/4 is 0.25. We subtract the lower exponent, which gives me this. I can move the decimal bigger there, which moves this smaller there. So that is Ka1. We are looking for pH, which means we need the H plus value. Write out the equation for the first H coming off. Here's the Ka1. It's going to lose some amount, destroy itself a little bit, and create the same amounts of each of these. We are ignoring the amount of H plus in the water originally as a little too small to bother with. We are ignoring the amount of H plus already existing in the water is too small to bother with at this point. For 8, I had the wrong stuff printed out, but here's the relevant information. We have 1e negative 3 moles of the weak acid in 1 liter. And here are the Ka values for taking off the first H and then the second H. So here's my dissociation reaction for the first H coming off. There it came off. And so this was the molarity that we started with. And of course, some of it was destroyed making some of this and some of that in equal amounts. And we can use the K value, K1, for taking off the first H to try to find pH. For pH, we need the H plus molarity. So that's what we're looking for here. X will be H plus molarity. So here's the original molarity. We're going to cross out X here because it won't add enough. It won't subtract enough to bother with. This times this is 1e negative 10, square rooted is 1e negative 5. X is the H plus molarity. Negative log of that is pH5. And the extra little trick to this is that if it's an even worse acid than the first time, then we're going to add so little H plus that it's not really going to matter and the pH isn't even going to move. The Ka2 is inconsequential and I'm not going to bother taking off the second H and doing the math on that. They really like these particulate diagrams. In this one, what they mean is that there's some amount of chemical that did not turn into ions, the plus and minus ions. And so I chose a weak acid. Some of the H's came off, some of them didn't. So not all the molecules dissociated, some of them are there. And then the ones that dissociated turned into H plus and HSO2 minus. In this one, all of them dissociated. And so I chose a classic supersoluble salt. And all the units are dissociated, so that could be what's in beaker B. On 10, I have a weak base with this molarity. It made a pH of 9. And so what I can do is write out the basic equation and where the A minus the whatever anion it is takes an H off of water and produces HA and OH minus. What is the value of one of these? I do know that this started at 0.1 and it lost something. However, I know more than that because it generated a pH of 9. The inverse log of negative 9 will give me the H plus molarity, which is 1e negative 9. And I can just sort of subtract the exponents out of 1e negative 14, or you can divide, and we get the OH minus molarity will be 1e negative 5. Now this should be equal to that because they were both generated together from the destruction of this. So this is the amount destroyed. However, when I put all this into KB, this amount subtracted out is inconsequential and I'm going to skip it. This times that is that squared, of course. This squared is 1e negative 10. And then it's divided by 0.10, which is the same thing as multiplying by 10, which means it gets less negative, and that's KB. I'll point out that if you write it as a hydroxy base and get this as your reaction, you get these numbers and you actually do get the same math setup. So it does work both ways. On 11, you can see all the corrections I made as I tried to dial this in, but I think we can follow along and get it. So you've added sodium nitrite, and that's not nitrate, that's NO2. So of course all the sodiums come off, but we're not talking about pH and so forth this time. So we're not going to just completely disregard it like all those other times. Now, NO2 is not the conjugate base of a strong acid, and it is possible for it to pick up some H plus out of water. So it is a base. So if this is the Ka of the acid version of NO2 right here, then Kw divided by Ka gives me Kb. Now, we're not going to actually do any math with this problem much. So I just want to note that Kb is definitely something I should consider. It's in the 10 to the negative 3 range, which means it does actually matter. So when I put this in, all the NAs come off and the NO2 minuses go into the water. So when you introduce this into water, what's the reaction that you get? Well, it's this. So some of this is going to destroy itself making that, and you get an equal amount of these OH minuses as you do of those. So just for dumb numbers, just pretend these numbers are roughly sort of true. I'm just going to illustrate how this would work. So you dump in 10 of these, you get 10 NAs and 10 NO2s. However, this one goes through a bit of a transformation and it turns into this. So whereas this one stays at 10, this one transforms itself into 9 or 8 or something. I don't even really care. My point is that its molarity is now less than that. So now we have our first two set up. This is definitely more than that. Now it made OH minus and HNO2 in equal amounts, but I will be extra picky and point out that there was a little OH minus in the water already. So this is more than that. And then there also was H plus, but not very much. Of course, only the amount as existed for OH minus at the beginning. And then these run around chewing up those, making water. And I assume that this amount added is not all used up. So this stays slightly above that. And this started out really low and only went down from there. So these three are definitely lower than these two. And again, the OH minus was made in equal amounts with that, but it got a little bit of a boost from there being a little bit in water. And I assume that the amount that it ended up being was still slightly greater than that, because there was so little H plus to even find. So this stays a little bit greater than that. And this existed very little in the first place and then only went down from there. For 12, what we would need to do is get something to attach to S minus 2. So if you put in a strong acid, it would be donating H pluses, and that would force this reaction here, this one, to go back toward HS minus, and then even further, that would make this go back toward the H2S. But in particular, reducing the S2 minus would be concentrating on this half of the overall acid reactions. And you'd be running this way because increasing the right side by increasing the H plus by Le Chatelier's principle would force it to the left. Now name a cation that's not ammonium. Well, one of the ones we discussed earlier, I think, was zinc. And zinc has a great affinity for hydroxide. So if you put zinc ion in water, what it does is it attaches pretty strongly to OH minus. And remember, because OH minus times H plus molarity must equal 1 E negative 14. If one goes up, the other must go down in direct proportion. So if this is going down, that's going up, which gives the same effect as what we just said. So it effectively, in a sense, donates H plus to this reaction, not because it has it, but because it lets water create more H plus through dissociation by removing OH minus from the solution. 13, we just find the biggest Ka and the smallest Ka and rate them. And it's really easy just looking at the exponents and just remember that this is bigger than that because they share an exponent. On 14, we want to know the lowest pH. That's the most acidic, right? Well, these are the conjugate ions of a strong base and a strong acid, so you can't get anything out of them. They won't attach to anything in water, so when you add them, you get nothing happening. K plus, again, is a repeat, nothing will happen, but the acetate ion would attract H pluses, so that would make a removal of H plus from water, and that would make a basic solution. The Na is the same thing as the K, because they are super solubles, both. NO2, though, as discussed back in number 11, will attract H pluses and stick to some extent, so that will remove H plus from water and create a basic situation. I changed this to Cl here to make it real clear. Ammonium is a supersoluble and will not attach to anything. However, it gets a little more complicated than that because it has H's to donate itself, doesn't it? Cl is the conjugate base of a strong acid, so it cannot attach to H+. You would be forming a strong acid in water, which is effectively an impossibility. And this is acidic. This does have an H to give because then it would form ammonia, NH3, which is a really common chemical. It's really stable. That does happen. This forms ammonia. Ammonia forms ammonium. And so if you put these two in, this will do nothing. And that one will donate some H plus to water, which makes an acidic situation. On 16, the general rule is that the non-oxygen atom that is the least electronegative will do the worst job of pulling electrons away from the H plus. That would make a weaker acid. So when I consider Cl versus I, just this half versus that half, half one, half two, and I compare I versus Cl, Cl is a whole couple steps up your periodic table and it's more electronegative. That means that it does a better job of pulling electrons toward itself. That effect cascades through. And the pair that is bonding to H plus will get pulled away from the H more. That makes the H less tightly bound, which makes it more acidic. It makes it a better acid. So this half is definitely going to be a better acid pair than this pair. Now, between these two, though, more oxygens has the same effect. Because of their electronegativity, they do a better job of pulling electrons to themselves, and what you get is an effect where the bonded pair of electrons to the H are pulled away, and three oxygens do a better job than two. So this is a stronger acid with a weaker bond to H than this one is, and the same effect here. As a matter of fact, that one should be the really obvious one because you should know your strong acid list, and that is a strong acid. So this is definitely stronger than any of the three, really clearly and far away. So here we have this weak base and a Kb. Well, we'll pretend it is anyway, right? So here's the base in water. It's grabbing H's off of water, making OH minus. This is the acid because it's missing the H now, isn't it? So this is the conjugate base. It's the thing that if it acted like a base, it would turn back into that. So how about we write Cb for conjugate base here? This was the base. It grabbed an H. So this is the conjugate acid. It's the thing that if it acted as an acid, it would turn back into the base. So how about we put Ca there for conjugate acid? So a sample has a pH. Now that's at equilibrium, so we don't have to do the whole minus X business. It has a pH of this. What's the molar concentration? So here's my methylamine, and it's a base, right? So it's pulling H's off of water and making that. That's just really a restatement of that. So what do I need? Well, the molar concentration of this. This is the X. This is the unknown. What's in the box? This molarity of this methylamine is the unknown. Well, this looks like something capable of a Kb expression to me. So if I could get these numbers, I could, and I know Kb, I could find this. So what do I know about this? 14 minus pH is POH because I need this, right? So then OH minus molarity is 10 to the negative POH. So this goes in here. Remember to put the negative back on or you will get a very wrong answer. Put this in the calculator and you get this. This is the molarity of that. Now, it's also the molarity of that because presumably these were made in equal amounts, and I'm going to ignore the amount that was in here from water initially because this is turns out it's a lot more, so it wouldn't matter anyway. So if I've discovered this number, that's also the value of this molarity because they were made together. Now I have something I can use because I was given Kb at the top. It's this. Products over reactants, the power of the number in front gets me this times this on the top. And then this, the unknown, is the bottom. So if I swap these two places, I get this times this divided by that, and I get the value of the base amount. On part B, we add in methyl ammonium chloride. So they give you the formula here. And what I notice is that it's got chloride on it. So this is the anion, that's the cation, this is a salt. It's dissolved. Oh, it's dissolved. They're all going to come apart. They give me grams. Ooh, that sounds like maybe they're not going to give me moles or molarity. I'm going to have to figure it out myself, maybe. I mean, why else did they give me grams? Usually that's what happens. And they give me a volume. So probably I'm going to have to generate my own molarity. That's a kind of a clue right there. So write the net ionic equation for this process. Well, the CLs all come off, and for the purposes of finding stuff like pH, they don't matter because they can't, of course, grab OH minus because they're negative themselves. They can't grab H because that would be forming a strong acid in water, and that's impossible. So this whole process and this idea is out. So for the purposes of, pH, we're going to ignore the chlorine. Actually, it's going to come back in a minute, but for the purposes of that, we're going to shove it to the side. So what I've done is donated the acid version, the cation, and that's got the H3, and they told us above that that's the acid version. So if I put this in water, it's going to act as an acid. And here it's donating H plus to water and we get a hydronium, or you can just do it the easy way and skip the water and call this H plus. You get all the same answers, so no one super cares which way you do it. So I am running this as an acid. Well, I can't run it as a base. It is an acid. So if I'm going to find pH, I'm going to have to find the H plus concentration, which means I'm going to have to find a Ka, not a Kb for this. Well, that's not too hard. Grab the Kb value that you were given and divide it into Kw, and you get Ka. So 10 to the minus 9, that is. Now, if I set up my icebox, I rewrite this essentially here, and I need a starting molarity, and then I know it's going to destroy itself somewhat, and then it'll make equal amounts of these, and then X will be subtracted out of whatever this is. Now, how did I get 4.93? Well, at first, I don't have that value, and I have a hole in my information. I need this, or I have too many unknowns, because I have this unknown and X unknown, and that's unsolvable. So what I need is molarity of this. I need moles per liter. Well, I essentially have liters right here. What I need is moles, but I have grams and I have a formula. And remember to put the CL back on. And I admit I forgot at first. And so I was disputing their molar mass. So if you put the CL back on, because was the formula for the grams with the CL on, then we can convert to moles and we can divide that by the liters. And that can give me a molarity. And that fits here. So it's this minus X and X and X, and Ka, which I found back here, is equal to these two, which are X, multiplied together over that. Now, with this kind of Ka, the amount that's going to be subtracted out from by subtracting X is immaterial. I'm going to cross it out. So I'm going to, this times that, that's going to move up, and square rooted gives me this, that's 10 to the minus 4. And what is X? It's the value of H3O plus or H plus, and negative log of that, that's negative 4 there, negative log of that gives me pH, which is 3.96. On 18, it tells you there's a buffer solution, and what you should be pinging in the back of your brain, or at least after we discuss it a number of times, is that you have a weak acid and its conjugate base, or you have a weak base and its conjugate acid. So what do we have? In fact, you can view it either way, really. We put in sodium OCl. So that's OCl minus, isn't it? Now that could act as a base because that could grab an H and we would not be making a strong acid. We would be making that. So if we're putting this in and this in together, we have a weak acid and the conjugate base. And that's a buffer, meaning that if I put in any more H plus, this can take it up. And if I put in an H grabber, it has one to grab here that's not off of water. And so it's hard to push the pH around in a buffer solution. That's the point of a buffer solution. Now, they determined the pH to be this. Fine. Well, note to self. So step 1, calculate the value of H3O. Well, okay, so pH is this. So the H3O plus, the hydronium, or H plus if you want, molarity will be 10 to the negative value of pH. So 10 to the negative 6.48, grab a calculator, and that is your hydronium or H plus molarity. Now also they told us, by the way, that Ka is this, and that's for the acid version, of course. Can't be for the base version. So which is present in higher concentrations? Well, this is an actual AP level problem. And also it's solvable another way. So it's up to you really to determine which way is easier. And also I have a little discussion about logs to impart. So this is the Henderson-Hasselbalch equation, usually written as A minus and HA for just as a standard form. So this is the acid version and this is the base version. However, we know exactly what the acid and base version are. So we could write them in like this if you want. Although technically, we could solve everything for this way if you wanted, because we're just looking for the higher concentration, which is present in higher concentration, the acid version or the base version. Well, let's put in values that we know. We know pH because they told me back here. We can find pKa because I know Ka and pKa will be negative log of that value. And we're just going to keep this here for a moment. What I'm going to do is say that I don't have two unknowns. I have one unknown, which is the value of the whole fraction. That's how I'm going to get out of solving for two unknowns at once. So let's solve for the fraction. Well, this is some number. It's that. And then if I subtract it over, I get this. Now they flipped it end to end, so we get log of the fraction is equal to this when I subtract that over there. Now, we'll have a log discussion in a moment, but this turns out to be a negative number. The only way for the log of something to be a negative number is if it's between 0 and 1. The value of this fraction must be greater than 0 and less than 1. It's a decimal with 0 in front. For it to be less than 1, which part is greater, the numerator or the denominator? Well, the denominator must be greater if the value overall is less than 1. And by that proof, HOCl is greater than OCl minus. But make a statement, because log of this is less than 0. Right? The only way to get a negative answer for a log less than 0 is if this is greater than that, is if this is greater than that, if the whole thing value, the whole value of the fraction is less than 1, this is greater than that, which means the whole value is less than 1. So what I can do to generate this number for real z's is I can undo the log and I say 10 to the power of both sides unzips log and gives me 10 to the power of negative 1.05. So grab a calculator and follow along, I would. 10 to the power of negative 1.05 is that. So that is now converted, this is converted to that, and that is equal to the fraction. But I know this number because it must be equal to that, and I found this back here. So remember, this is equal to that. So I can say that I'm going to swap these two. The unknown molarity that I want is equal to that divided by that. And I get 3.8 times 10 to the negative 6. Now I can solve it another way. Let's set up our equilibrium expression, right? And let's say that I remember I found this from the pH, and this must be made in equal amounts. So these numbers are the same. And actually, you can just go and do it this way. And in fact, this way might be easier. What's this value? I don't know. Ka was given to me, and it's equal to then these two squared over that. So I'm going to trade these two. This squared divided by that is that. X is the value of that. X is the value of that. And look, I'm only off by about 0.1 in my answer, and it's immaterial really in the end. And it's certainly good enough for this question because the question isn't even the value, it's which one's greater. And this value is definitely greater than that value. In fact, it's over 10 times as much. So there are two ways to attack it. It depends on which way you want. This might be clearer for a lot of people. You don't have to do it with Henderson-Hasselbalch. This leads me back to a discussion of logs, though. Log means 10 to the what power will get you the number you're talking about. So what's log of 0.5? This leads me to a discussion of logs, though. There are essentially only three categories of numbers you can take log of. You can take it for less than 1, exactly 1, or over 1, and there's some breakover points in there. Now, somebody will say, well, what about 0 and under 0? But go ahead and try it on your calculator. The log of 0 is undefined. It's math error. You can't stick an exponent on 10 and get 0. And you can't stick an exponent on 10 and get a negative number. So those two other categories out here of 0 and less than 0 are impossible. They're not logically possible. So we're going to throw them out and say these are the only three possible categories. You can have under 1, 1, and over 1. So if it's under 1, for instance, maybe it's 0.5, you're saying 10 to the what power will get you 0.5. Now grab a calculator and do it. What's in the box? The calculator returns negative 0.3. The exponent that you stick on 10 to get a number less than 1 will be a negative value, which actually we've been doing quite a lot. Log of 1 means 10 to the what power will get you 1. What's in the box? What's the exponent in the box? It's 0. And you can try it on your calculator. In fact, anything to the 0 power is 1, so you don't even need to know what this is. What exponent will get you 1? Well, 0 is the answer universally. What about over 1? For instance, maybe it's 100. 10 to the what power will get you 100? What's in the box? What exponent on 10 will get you 100? 2 is in the box. 2 is the exponent there. So in these cases, you get a negative answer for log. In this one, it's always 0 by definition. And in these cases, the answer is positive. So when we got a negative value for the answer to a log problem, I know that I must be taking the log of a number under 1, because when I took the log of a number, I got a negative value. Why would I be getting a negative value for a log answer? It's only true if the number under discussion, this number represented by the fraction, is between 0 and 1, which means the denominator must be greater. And that's our answer. Which one is greater? This one is greater, which is why they're saying log of the fraction, the unknown number overall, is less than 0. It's a negative number. The answer is a negative number. So this must be greater than that, because you must be discussing a number as the fraction that is less than 1.